So this lesson, we're going to be looking at trigonometry and polar coordinates. So there's a lot of words at the beginning, but I think reading them is going to really help you kind of understand what polar coordinates are. So if we wanted to travel from one location to another, there are several different methods we could use to travel, such as walking, biking, driving, flying, boating, etc. Each method has its own advantages and disadvantages depending on the particular situation. Additionally, each method has specific constraints and restrictions. If we were driving from one location to another, we would have to stay on the roads, which are generally formed by a rectangular grid system. If we are flying, we would be able to fly in a direct path to our destination, provided there was an airport. Plotting points in space and defining functions is not much different than transportation examples above. There are several ways to define points and functions in space, each with their advantages and disadvantages. Up until this point, the only system you have learned has been the rectangular coordinate system. This system uses an x-axis and a y-axis, and the points are described using an ordered pair x, y. This rectangular coordinate system, which is also called the Cartesian plane, is very similar to a road grid, where you have to go over and then up to define a particular point in space. An alternative way to describe a point in space is the polar coordinate system. With polar coordinates, we do not use x and y values to define points. The polar coordinate system is much more like flying an airplane. To define a point, we only need to state the angle of the point in standard position and the assigned distance of the point from the origin. In other words, we simply rotate until we are facing the point and then draw a line directly to the point from the origin. The polar coordinate system can be very useful, especially when working with circles, trig functions, and conics. In the polar coordinates, the point A is defined by r, theta, where the absolute value of r represents the radius of the circle on which point A lies, and theta represents the measure of an angle in standard position whose terminal ray includes point A. One really cool result of using polar coordinates is that the same point can be represented many different ways. All right, so here is a polar graph. So it kind of looks like a bullseye. And so the angles that we're going to work with are going to be the angles that we kind of focused on in the unit circle. So I'm going to go ahead on this one and just go ahead and label those angles. There will always be one that we're going to skip that is close to the axis, because this is going in twelfths. And pi over 12 isn't really a special angle, but they just use it to kind of, I guess, make it evenly spaced. But we know that straight up is going to be pi over 2. All right, then we're going to skip a space. The next one is going to be a pi over 3 angle in quadrant 2, which is going to be 2 pi over 3. The next one is the pi over 4 angle in quadrant 2, which is going to be 3 pi over 4. And then the pi over 6 angle in quadrant 2 is going to be 5 pi over 6. Right, and then we'll skip the next one, and then straight to the left is going to be pi. Right, and then we'll skip one, and then it's a 7 pi over 6, 5 pi over 4, 4 pi over 3. Okay, and we'll skip one, and then this is going to be 3 pi over 2. Skip one, 5 pi over 3, 7 pi over 4, and 11 pi over 12. Nope, 11 pi over 6. All right, so let's plot some points. So for A, we have the R is 2, so this point is going to be graphed on this, I didn't draw that great, but on this circle that has a radius of 2, we're going to go to the angle that's pi over 3. and that is going to be point A. So you just find the angle, move the distance, and that's your point. All right? And then for B, we are going to be on the circle that has a radius of 1. And we're going to go to the angle that's 3 pi over 2, which is that one right there. So this point here is point B. Right? For C, we're going to use this outside circle that has a radius of 3, and we are going to go to the angle 4 pi over 3, which will be this one, C. All right, D gets a little more complicated. So this is pretty straightforward until you start having negative coordinates. So on D, we have still positive 2, so that means we're going to use this angle, or we're going to use the circle 2, but we're going to rotate negative pi over 6. So normally we would rotate this to get to pi over 6. But since it's a negative angle, we're going to rotate this way. So that's going to be point D. All right. All right, so let's do another example. I'm not going to go through and do all the points this time because we just don't need them. And we could. I'm just going to try and save some time. All right, so the first one is super straightforward. We're going to go to circle 2, and we're going to rotate pi over 4. So we're going to get to this point right there. That's going to be A. All right, B tells us to go to circle 2, but this time we're going to rotate negative 7 pi over 4. So positive 7 pi over 4 is here. So we're going to rotate this much, but we're going to rotate in the opposite direction. So it ends up leading us right back to where A was. All right, for C, we are going to still be at 2, and we're going to rotate 9 pi over 4. So a full rotation is 2 pi. So 2 pi would be 8 pi over 4, and then we need to rotate another pi over 4, so it looks like it's also going to take us back to that same exact point. And probably the most difficult ones to do are when the R is negative, because it's just kind of different. But when R is negative, instead of starting here for your rotation, you're going to start here for your rotation. All right, and we're going to from here, we're going to rotate 5 pi over 4. So the angle 5 pi over 4 is here. So the normal rotation is this much. So we're going to start here and do that 5 pi over 4 rotation, which I know is probably not a big surprise. It takes us right back to that same point. So that's 4 different ways to represent the exact same point. So example 2 illustrates how a single point in polar coordinates can be expressed in many different ways. In fact, there are infinitely many ways to represent a given point using polar coordinates. So on example 3, we're going to plot the point 3, 5 pi over 6. So right here is the angle of 5 pi over 6. So 5 pi over 6, we go to 3, we rotate that much to get to that point. Okay, and so we can try to think of some other ways to get to that point. So obviously our R has to at least have an absolute value of 3. It could be a negative R. We could do different things. So we could use a negative 3. And then rotate in the negative, also rotate in a negative direction. So that angle is the same as this in the negative direction. So that would be negative pi over 6. So that's one way we could do it. Another thing we could do is keep it positive 3 and rotate in the negative direction to get there. And so I know this is a half rotation, which is pi. And then it looks like we go another 6 pi over 6. So that would be a negative 7 pi over 6. Right? Now, and there's more we could do. So sometimes you can just plot the point and just figure it out like we did right there. If you don't want to do that, the other thing you can do is I'm going to give you 3 different like mathematical things you can do to get different points. One, we keep r the same, but then we take the theta and we subtract 2 pi from it. Now, if we did that, this is what they would give us. This is, for this particular example, this is what we would get. Right? Or you could do the opposite of r and then take theta and add pi to it. I didn't give that example. I'll do that in just a second. Or we could take negative r, take theta, and subtract pi from it, which is what that would give us. Right? So let's just do this purple one. If you're one of those people that just really just wants a formula to follow to do each time, we could take r, and we could, which in this case is 3, and we could do the opposite, and then take 5 pi over 6 and add pi to it. Now, hopefully by now you guys know whenever you add fractions, you need a common denominator. And so pi is the same as 6 pi over 6. And so our final answer, when we add that, would be negative 3 and then 11 pi over 6. So let's just make sure that does work. So negative 3 means we would go over to this point and we would rotate 11 pi over 6, which is almost a full rotation. It's pi over 6 short of a full rotation, so that also would get us that point. All right, so it's up to you. When you're asked to do this, if you want to just graph it and figure it out, you can. Or if you wanted to, you could use 2 of these 3 algebraic forms to figure it out. All right. I know there's a whole lot that we're learning in this one lesson today, but one of the things we're going to do is go from rectangular coordinates, which use x and y's, and change to polar coordinates, which use r's and thetas. All right, so to do that, we're going to use some old trigonometry rules that we know. Hopefully you still remember that cosine of theta is found by taking x and dividing it by r. And so if we have polar coordinates using x and r, and we want to, using theta and r, and we want to change to x, I can solve this for x by multiplying by r. And x is always going to be r times cosine of theta. All right, and then hopefully you remember from trigonometry that sine of theta is the y divided by the r. So if I want to solve that for y, I would get that y is equal to r sine of theta. Okay, so we're going to convert these polar coordinates to rectangular coordinates. And so for the first one, I'm actually just going to use common sense. And then don't worry, we'll use the formulas plenty. But 2 pi means that if we were looking at this, you would go to circle 2 and you would rotate pi. So that means that 2 pi is just this point right here. All right, so it's 2 circles out, or the radius of it is 2. So if I wanted to change that to x's and y's, this point here is just 2 units to the left. And when we're talking about x and y's, that's the ordered pair negative 2, 0. So if you can do it in your head, I'm perfectly fine with that. These next two we're not going to be able to do in our head. They're not integer coordinates, or maybe 1 or 2 might be integer points, but we're going to have a lot of square roots and a lot of fractions that we're dealing with here. Okay, so the point 4, where r is 4 and theta is 5 pi over 3 would be, well, we don't go to 4 on these circles, but it would be some point like out here. All right, so if I want to change that, I want to change that to x's and y's. X is going to be equal to r times the cosine of theta. All right, that's just this formula right here. These are very, very important. Whoops, wrong one, sorry. This formula right here. All right, so we would want to pull out our old unit circle, or just somehow pull out of our brain what the cosine of 5 pi over 3 is. So the cosine of all of the pi over 3's are either going to be 1/2 or negative 1/2. For 5 pi over 3 it is going to be positive 1/2. And I'm not really sure why I wrote a 5 there, but it should definitely still be a 4. So the x coordinate here is just going to be 4 times 1/2, or 2. All right, and then when I want to do the y coordinate, y is going to be 4 times the sine of 5 pi over 3. Right. And then the sine of all the pi over 3 angles is going to be the square root of 3 over 2, or negative square root of 3 over 2. For 5 pi over 3, it is negative square root of 3 over 2. Right. And then that 4 over 2 is going to reduce to 2, so this should end up simplifying to negative 2 square root of 3. And that is your ordered pair for your answer. X, y coordinates. All right. So this is a point in the polar coordinate system. This is a point, the same exact point. That would be the same exact point in the rectangular coordinate system. So going out to circle 4, rotating to 5 pi over 3 is the same as going right 2 down negative 2 square root of 3. All right, so let's look at this one. This is r and theta. If I want to find x, I'm going to do that x is equal to r times the cosine of theta. All right, and the cosine of all the pi over 6 angles is going to be square root of 3 over 2. For 7 pi over 6, which is in quadrant 3, that's going to be negative square root of 3 over 2. All right, and this doesn't really simplify much, but the negative times the negative is a positive. All right, and then y is going to be negative 3 times the sine of 7 pi over 6. All right, and all sines of pi over 6 angles are either 1/2 or negative 1/2. In quadrant 3, sine is going to be negative 1/2. So that's going to simplify a little bit to 3 pi over 2. So the rectangular coordinates for that point are 3 square root of 3 over 2, comma 3 over 2. All right, and we are going to have to go the other way as well. So sometimes we're given x's and y's, and we need to change them to r's and thetas. And so whenever we need to find r, we are going to use this old rule that x squared plus y squared is r squared. And whenever we want to find theta, we are going to use that the tangent of theta is y over x. Now, I am always going to graph these rectangular coordinates first, just a little baby graph. And so I'll know what theta to use, because there's going to be 4 different angles that have that tangent. And so we just have to make sure we choose the one that's in the right quadrant. So, for example, 5a, I have the point negative 2, 2. So left 2, down 2. That's our point that we're trying to find the polar coordinates for. So we're starting off with x's and y's, and we need to change to r and theta. So to get r, we're going to do x squared plus y squared equals r squared. So 4 plus 4 is 8. So r is going to be the square root of 8. We're just going to leave it like that. All right, then I want to find the angle. So to find the angle, I'm going to say the tangent of theta is equal to y over x, or in this case, the tangent of theta is equal to -1. You know what? I graphed that in the wrong place. Sorry. We're going to go left to up 1. All right, so I know the slope of this line is going to be -1. So there's actually 2 angles on our unit circle that have that slope, and it's going to be they're definitely pi over 4s. So our answer could be 3 pi over 4, or it could be 7 pi over 4. But we're looking for the angle in quadrant 2, now that I have it graphed right. So the angle in quadrant 2 that has that tangent is going to be 3 pi over 4. All right, so the polar coordinates for for this point right here that you go left to up to, you go to r of square root of 8, and you go to angle 3 pi over 4. That's a direct route to that point. All right, so let's do it again. Let me make sure I graph this one right. I'm sorry. So this is a x and this is a y. So we're going to go right 1 down square root of 3. So we're looking our angle. When we get our angle, we definitely need to choose an angle in quadrant 4. Okay, so we have x squared plus y squared is equal to r squared. So 1 squared is 1. The negative square root of 3 squared is 3. So it looks like r is going to be 2. All right, and then when I want to get my angle, the tangent of theta is equal to negative square root of 3 over 1. So I'm looking for an angle in quadrant 4 that when I take the x and I multiply it, when I take the y and I multiply it by the reciprocal of x, I should get the square root of 3. So I'm wanting to find the one that the square root of 3, the y has the square root of 3. So the square root of 3 is on the top, not on the denominator. And so that is going to be 5 pi over 3 for our angle. All right, so the polar coordinates that take you to right 1 down square root of 3, the direct path to that is going to circle 2, angle 5 pi over 3. All right. And then for this one, when I do this graph, over 0 down 5, that is my point. Now, when it's on the quadrant, I wouldn't do any of that stuff I just did. I know that I go 5 units down to get there, and that angle is 3 pi over 2. So I just go ahead and I know that r is 5 because it's 5 units down, and it's at angle 3 pi over 2. All right, finally we're to the last page, and the last page is on complex numbers. And you guys learned a little bit about complex numbers earlier in the year. Complex numbers involve the imaginary unit I, and if you guys remember, I is equal to the square root of -1. So anytime you're taking the square root of a negative, it creates an imaginary or a complex number. A and B are both constants. So a complex number can be understood as a point in the complex plane. And it can be determined by corresponding rectangular or polar coordinates. So when a complex number has the rectangular coordinates 3 or A and B, it can be expressed as A plus BI. So for example, the complex number 3 plus 2i can be represented by the point 3, 2 in the rectangular coordinate system. All right, we are also going to represent it in the polar coordinate system. So because earlier we talked about that x is equal to r cosine of theta, and y is equal to r sine of theta, we can use that to be our x and our y, or our a and our b, I guess I should say. So a is going to be r cosine of theta, because that represents the horizontal coordinate, and our B is going to be our sine of theta, because that represents our vertical coordinate. All right, so this is going to be very much like what we just finished doing. All right, so a complex number is represented in the complex plane. The complex number has rectangular coordinates -2, -2. So that is going to be right here. All right, so we want to express it using r and theta. So r, or we can say x squared plus y squared is going to be r squared. So this is very similar to one we already did, where r is the square root of 8. All right, and then I know since I moved the same over and the same down, this is going to be a slope of 1. And so I know it's going to be the pi over 4 angles that have that slope. So I already know that the pi over 4 angle in quadrant 3 is 5 pi over 4. So if I want to represent this using polar coordinates, I'm in this place. I'm going to take this formula right here. In the place of r, I'm going to put the square root of 8. And then in the place of theta, I'm going to put 5 pi over 4. Oops, sorry. Let me fix that. Oh my goodness. Let me start over. In the place of r, we're going to put the square root of 8. And then it's cosine. And then in the place of theta, we're going to put 5 pi over 4. There we go. And then plus I is that imaginary unit. And then in the place of r, we're going to put square root of 8. In the place of theta, we're going to put 5 pi over 4. All right, and then we're going to go the other way also, and so this time it's represented polarly, and then we're going to represent it rectangularly. And now we need x and y. So x is going to be 4 times the cosine of 7 pi over 6. The cosine of 7 pi over 6 is going to be negative square root of 3 over 2. So it looks like our x coordinate is -2 square root of 3. All right, for y, it's going to be 4 sine 7 pi over 6, or 4 times -1/2, or -2. All right, and so this complex number would be -2 square root of 3 minus 2